Hello, everybody, and welcome to episode 30. We've done 30 of these. Episode 30 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that over there is Gavin. Gavin, how does it feel to be 2010?
What 20? I
Like
don't
there's
understand.
28, 29, 2010. We're up to 30.
Oh, I mean, I'm reminded of. Have you seen Bo Burnham's Inside yet?
I have only watched the first couple minutes of it.
He
It
sings a
wasn't,
song about turning
yeah.
30 because he turned 30 while making it,
Oh, did he
and
really? Okay.
it is an excellent song.
Is it?
You need to finish watching it so we can talk
I
about it.
I heard so many good things. I started watching it and it was like it wasn't quite my thing, but I heard so many good things that I do want to give it another shot because I like Bo Burnham and it was
It
one of
is.
those
It
things
is
where
definitely different from his previous work.
right, right, but he is, you know, I don't know if I quite want to call him a genius, but he is a national treasure. I guess I will go as far as to say
All
that.
right. All right.
So we are. I am looking forward to our episode today, mostly because I don't know what it's about. Because there's nothing in our note sheet. Before we do there, obviously take a look at the links down in the description. If there's anything from our notes from our show today, they'll be down there in the notes, as well as our Twitter account, Gavin's blog, some forms to fill out, all that fun stuff. If you hear anything weird going on in the background, that is my girlfriend's dog that I'm currently keeping an eye on and is trying to bite me, which seems a bit unnecessary, but just so you know, that might be happening. Um, but with all of that out of the way, we can go ahead. Let's do our This Week of Science. Gavin, what was happening? I'll go with 2012. At some point in 2012, This Week in Science.
Well, that's a bit of a trick question, Mike, because we're actually not doing one this week.
So can I be right technically because I wasn't wrong?
How about you were not right, but you were not wrong.
I will gladly take that zero. So we're not doing This Week in Science?
Not this week,
Okay,
because
so
there was a relatively large piece of paleontological news that came out in the last week that I wanted to talk about.
oh boy.
Because the news itself didn't bother me. All of the coverage around it did.
Okay, so this is like a media criticism thing
Yes,
rather than a paleontology. Okay.
yes. So
Well,
you
you
may
go
have
for it.
seen stuff shared around social media about a new study about the dinosaurs and how they might have been declining before the asteroid hit.
I missed this one, but I will take your word for it.
Oh, I can hear the pupper in the background. Oh.
She's very sad about all the dinosaurs that are declining.
Yeah, so there was a new study published just in the last week or so. I believe June 30th is the day that it was actually published. That said, roughly, that dinosaurs were already sort of declining and struggling a bit before the end Cretaceous mass extinction that we've talked about a few times here. And if you remember back to our, I believe, episode 2 about dinosaurs, I did sort of mention that some people do, that is something that is talked about a bit when talking about dinosaur paleontology.
Right. It's it is not quite as simple as we know for 100% certain that asteroid killed every dinosaur. There was a lot of things that could have been going on, and it's ripe for academic debate amongst people that are not crazy.
Right. And so there was a new paper published by some very reputable people. One of the people, I don't believe that he is the lead author, but he is on the paper. His name is Michael Benton. He is based out of the University of Bristol in England. And he is a very well-known paleontologist who works a lot with a very large database. Completely open source. Anybody can look into it. It's called the Paleobiology Database. And basically, any person who publishes a paper, say, I publish this paper saying I found this, species of whatever, could be a fish, could be a bug, whatever, could be a plant. They will take the information from that paper, say, okay, what was the thing? What's the name of the formation you found it on? What age was it? What is rough, because a lot of scientists don't like to give out the location of their fossil localities. So, like, what are the approximate latitude and longitude? And they will convert that to a paleo latitude and longitude whenever that rock was supposed to be from. So, if it's at the equator today, that doesn't necessarily mean that it was at the equator whenever it died. So, very large, completely open source database. He's very well known for working with data from that, which is what they did for this paper. And long story short, they looked at a total of around 1,600 total fossil occurrences. So that's just essentially different specimens. And again, this is all through a database. They didn't actually look at the specimens. From just under 250 total species throughout the entire Cretaceous period, almost 100 million years worth of time. And they basically conclude that based on the rates of sort of speciation, the sort of appearance of new species, that seems to be going all hunky-dory at the beginning and sort of the middle of the Cretaceous period, but then it decreases about 10 million years before the extinction, around 76 million years ago, when sort of the origination of new species, the appearance of new species, declined quite a bit. And so most people only kind of saw that, including seemingly professional science writers from very reputable sources, at least in my opinion, from sources such as CNN or Live Science. And they sort of note a couple of things, that the main criticism that I talked about in our episode about dinosaurs with this, and that I have with this study in general, and which, to the author's credit, they fully recognize where that this is a potential error, is that almost all of the very latest Cretaceous, right before the asteroid hit, all of the dinosaur material, with maybe one or two exceptions, comes from Western North America.
So everything they were studying came from just one part of the Earth?
No, they were looking at stuff globally, but it's like we only have fossils from this area right before the asteroid hit. So just inherently, you're only getting a snapshot of that area at the time. We don't have, Australian dinosaurs from this time. They just don't. We don't have them, so they inherently are missing from this data set. So for all we know, Australian dinosaurs could have been doing completely fine.
Okay. And so explain to me again what the media got wrong about this.
They pretty much put that little part as a footnote, which I get it. You're wanting clicks for your article. I get it. I have a blog. I write articles. I understand. The thing that really bothers me is the fact that almost all of them, particularly in their headlines, even if they do sort of contradict or contradict themselves a little bit throughout the body of the article, make it seem like, okay, it's settled. This one
Oh,
article settles it. Dinosaurs were declining, for sure. When it's like, no, that's not how science works. One article being published does not suddenly mean, okay, cool, everything's settled. And which, they have a really diverse data set here. Like I said, 1,600 different fossil occurrences, 250 or so different species, spanning 100 million years, give or take. A pretty robust data set. That's about as robust as you can get in paleontology. But that there are some really important holes in this that just seeing the article, the vast majority of people don't read the articles. They just see a cool headline that they think is neat and then click the share button on Facebook or what have you. And it's really just misrepresenting science.
and to be clear, this is the problems you're talking about. Like were identified in by the authors, right? Like you know they didn't you say they were kind of like upfront with potential problems or further areas of study that are needed with this paper.
Right. And like the authors, always in like their conclusions, will say, here are some potential holes in this research, but we still believe in it despite these. Otherwise, we wouldn't have published the paper. And I think this one person who, to the person who wrote this particular CNN article's credit, talked to some people who were not involved in this study, so talked to other people. One person says, and this is a direct quote from Joseph Bonser, a doctoral candidate at the University of Bath, also in England, I believe. Quote, there are huge biases in the fossil record due to a number of factors, mainly geographical and economical, which we will talk about in a future episode. But also more personal biases like paleontologists focusing on looking for one species, for example, like Tyrannosaurus, which is absolutely true. The main reason why we know North American paleontology so well is because North America is relatively wealthy compared to the rest of the world. Some of those fossils may exist somewhere in Africa or in certain parts of South America, but those places have not been as thoroughly explored, and paleontology is not something as invested in those countries because they are relatively poorer countries relative to like Canada and the United States. Continuing the quote, the fact that multiple groups of scientists working on the exact same question at the same time can come up with completely opposite results further enforces this. That there is a great need for further data collection, i.e. digging up more dinosaurs and finding out where they lived and how successful they truly were. So the jury is very much still out on this, but based on the majority of articles that I've seen, that would not be the interpretation you would take away.
Pardon me. And that, that's going to wind up leading to a whole bunch of people having just a misunderstanding of what the article says, how science works. Like, it seems like there is a whole bunch of things that are being wrapped up into, the misunderstandings that are on full display here.
Exactly. And to some people's credit, there are some, especially like people who write articles, like science communicators who focus particularly on dinosaurs. For example, there is a wonderful science communicator named Riley Black. She is excellent on Twitter. I don't know her Twitter handle off the top of my head, but we can find it and link it in the show notes. But I would assume that she wrote an article about it. I didn't see it if she did. But she was very vocal on Twitter, basically saying similar things to what I'm saying here, where it's like, this was one article, man, like, or one paper. That doesn't mean that like this is the only way to interpret these data.
So do you think that, like, was this a bad job by the media? Is the media, at large, are they ill-equipped to handle the story? Like, there's no way for this to be handled appropriately. Like, if you were to kind of prescribe a remedy here, is there a way to fix this kind of problem without, under the existing structures of, the way science media works?
I think that it might be even less of like the actual people writing the articles as opposed to maybe their editors being like, this isn't clicky enough, because that's what our
Absolutely, yeah.
media has devolved into.
Right, exactly.
So there are many very good science communicators in the world and science writers. And so the fact that so many of these articles were so ever present in paleontology circles over the last week has just been very frustrating to me.
And that's part of why we started this podcast. And you have your blog and the Twitter account, which everyone should follow. Like, that is part of why all of that exists, is to, try and go a little bit deeper than surface level on all of these things.
Exactly.
And so, speaking of going more than surface level, so our actual topic for today, does it have any relation to this, or was this just something you need to get off your chest?
Tangentially, I knew that I wanted to do this little rant at the beginning, so we're going to be talking about a particular group of dinosaurs today. My favorite group of dinosaurs, the sauropods.
The sauropods. All right, so I guess that we can get into it.
Yeah, so sauropods are one of the most iconic types of dinosaurs, but they're a lot of times, sometimes people's like least favorite. And to me, I don't really get that because they're not the ones, they don't have horns, they don't have big teeth or anything. They are the big, long neck, long tail guys.
Long neck, long tail.
Littlefoot from The Land Before Time, if you remember. Or,
Okay.
as more people might remember, the first dinosaur that you see in Jurassic Park, the one that is, just kind of standing there as tall as a building that they just don't happen to notice until they're right on top of it. That is a Brachiosaurus. That is a type of sauropod. That is the general type of dinosaur we're going to be talking about today.
And I assume that there's, several subtypes.
Oh, you know it.
I am looking forward to it. So, I have no notes for this episode. I am going in totally blind, and it is Gavin's favorite dinosaur. So, we're all in for a treat, especially me, but hopefully everybody listening at home. So, let's go ahead and get started.
Absolutely. So let's just give some of the quick stats, the stuff you might see on the back of the Sauropod baseball card.
All right. Now we're talking my language.
So, sauropods as a group show up somewhere in the late Triassic, maybe a little earlier, but generally around 215 or so million years ago, and make it all the way until the end Cretaceous mass extinction. They're around for over 150 or somewhere in that general vicinity million years. Very long time.
Significant.
They basically are by far the largest group of land animals ever. And it's not even close.
Now, largest group of, do you mean like most number of them? The like largest in terms of mass? What do you mean by largest?
Like size. Like they are big.
Okay.
So, if you remember back a couple episodes to the elephants episode, we talked about some real big animals. Our largest land animal today is the African bush elephant. They top out, largest individuals are somewhere in the vicinity of 10 and a half or so tons. Some of their largest relatives could have been pushing 15, maybe 20 tons.
Okay, and how big are we talking for these boys?
That's about the average for these.
How big? Say that one more time.
That's about the average
No,
for
like how
sauropods.
big? Because I thought you were still talking
About
about
20 tons.
Oh, okay, 20.
And so just to
That's
sort, and also, maybe you might be thinking, okay, well, they're dinosaurs. Every dinosaur was pretty big. And like, not every dinosaur, but in general, there were a lot of big dinosaurs. But just sort of, for example, the general size estimates, at least sort of weight estimates that you see for things like T-Rex, somewhere in the realm of 7 tons. Similar range, maybe a little more toward 8
7
tons.
tons, by the way, still huge.
Oh, still huge. That is a very sizable elephant. Obviously, they're very different shaped animals, a T-Rex and an elephant.
Right, but still.
Triceratops and their cousins, somewhere around there, maybe pushing 8 tons. Some of the really big duck-billed dinosaurs, maybe somewhere like topping out at 12, 15, somewhere in that range. Not even the largest of any other land animal, which is an important asterisk. No other land animal, in terms of like average size over the history of their group, even comes anywhere close. So like the next largest animal after elephants today are rhinos. And think of just like the size difference from a rhino to an elephant. That is about the leap you need to make from an elephant to the average sauropod.
What's going through my mind now is how does an animal consume enough food and calories to get to that to get to that size, because that's so much, and I'm assuming that there's going to be a lot of them all in the same place competing for food.
We
Like
will
that is
absolutely talk about that.
let's get to it, because I am so ready for this. That's massive.
So that is well, but before we move on, I want to hit some of the highlights
Oh,
of.
that wasn't a highlight.
Oh no, some of
All right,
the
hit
biggest
me.
members, and these are like the tippy top, may have been somewhere in the vicinity of 60 to 80 tons
60 to 80 tons.
for one individual animal. Yes.
That, I mean, we've talked about this in other like there's reasons animals don't get that big. It's wildly inefficient, and yet, yeah, I don't even know. I don't know what to say. That's just
We
nuts.
will break it down, but again, there is nothing even close. Sometimes in a lot of books that I had as a kid, you would see like they'd have like a picture of a giraffe just because it's like, okay, that's the only thing that we have today that's got like a really long neck and is tall. They're not even comparable at all. We have nothing today that even comes close to doing what these did in their ecosystem, to changing their ecosystem in the ways that we think they did, and to just being that large of a mass. Nothing even comes close,
Nothing on
with the
land or
exception of
not.
whales.
Okay, I was gonna say, because I assume that like water animals had a bit of a leg up just with how
Even
gravity works.
still,
But yeah,
there are very few aquatic animals that get this big. Even the largest, like mosasaurs, that or plesiosaurs, which we've talked about previously, um, they did not even get close to this large. Not even close. The only thing that gets as big or bigger are the modern, I believe they're called rorqual whales, things like blue whales, or rorquals, my bad. Things like blue whales and the big filter feeding whales. That's pretty much their only competition in terms of size.
so when it comes to competition, you said, like, did they have any? I'm assuming they didn't have any like natural predators, and I know that's probably difficult to discern, from all from that far ago. But like, I assume these guys could just kind of do whatever they wanted, right? Like, who was gonna mess with them?
We will circle to that in a bit.
Okay,
So now we're moving on from the baseball card.
all right.
So let's talk about sort of their evolution and how they got to be some of these immense, herd of elephants per individual animal sized animals.
Do we have a good view of their evolution, or is this one of those ones where there's some pieces missing?
We have an excellent view of their
Oh,
evolution.
yes, one might call it outstanding.
Absolutely. So, which is, makes sense because they're big. Big things tend to fossilize much easier than little things. And so them being big is very helpful to us as paleontologists. So, before we talk about sauropods proper, that we need to talk about sort of a little bit of like how dinosaur divisions work. So, most people agree that there are two big divisions within dinosaurs. There's one group called Saurischia, which means lizard hip. That includes your theropod dinosaurs, your T-Rex, Velociraptor, and such, the two legs, or walk on two legs, eat meat, those kinds of dinosaurs, and the
Okay.
sauropods. Then the other branch are called the Ornithischians, which means lizard or bird hip, and those are pretty much anything else that's a dinosaur. Your Triceratops and friends, the ceratopsians, duck-billed dinosaurs, things like ankylosaurs, the big like armored tanks with the club tails, things like Stegosaurus and friends. All of those are ornithischians.
Right, that name sounds familiar from previous episodes.
Right. So that the Saurischian side is where we see sauropods. So their closest relative as a group are the theropods, T-Rex and friends. Not the most obvious things to be relatively closely related to,
Mhm.
But there are people who contest that, but that is sort of the general consensus right now.
Okay.
But sort of within that, before we get to sauropods, we have what's called the Sauropoda Morpha. Basically, sauropod shape is what that means. So sauropods are a member of this, but there are members of this group that are sauropod shape, but not true sauropods yet.
Okay.
These look much more like your very first sort of primitive dinosaurs. And I think I actually mentioned this in our episode about dinosaurs. The default condition for dinosaurs is walking on two legs.
I do remember you saying this, yes.
So, and sauropods were no exception to that. The very first sauropod ancestors, after they split off from theropods, walked on two legs and had, grabby hands. But they're sauropoda morphs because they start to be like trending that way. They got longer necks, not nearly as long as we see later, but longer. You would see that animal and be like, hmm, is there a snake coming out of there or what? Um, Whereas, with the later ones, you'd be like, is there a python coming out of that animal? As opposed to just like, wow, your neck's a little long.
Yeah,
So,
right.
and also their back legs tend to get a little thicker for more weight bearing. They tend to just also get larger. They sort of show up, the sauropodomorphs, in like the middle Triassic, around 230 or so million years ago, roughly the same time as we mentioned last episode that pterosaurs also start showing up.
Mm-hmm.
We have really interesting evidence about these first sauropod ancestors slash cousins. We know that they had gastroliths, which are stones that they eat. They keep stones in their stomach to help grind up their food. A lot of birds and actually quite a few different kinds of lizards and reptiles and other things will do this as well.
Do the stones get digested eventually as well, or are they strictly there to digest or to help with digestion, but they don't actually get digested themselves?
Nope, they get passed. They get pooped out.
Huh.
As far as I can tell. Which is why, they don't really eat ones that are huge.
Right.
um, but you can tell that that's what they were for, and not just rocks that happen to fall into the skeleton after it died, because they
Mm-hmm.
tend to be very rounded and very smooth, just because they're constantly grinding on each other to like mash up the food.
Makes sense.
Uh, and you see that with a lot of things that eat food that is not easily digestible. That helps extract more nutrients out of them, things like that. Uh, and so we think that these ones also might have had a little tiny bit of a beak as well to help with just sort of shearing off, plant material, things like that, to be ground up in their stomach. Not super big, and they kind of hang out for a little while until we get to sort of the next step of almost sauropods, but not quite, which are called the prosauropods. Pro in science and biology usually
Like
means sort
proto.
of in front of.
Okay.
So the prosauropods, which isn't, I believe, technically an actual group. I think that's just sort of an informal name. But they are much more sauropod-like. They get much, much larger, including things that if you've ever seen Walking with Dinosaurs, the sort of late 90s, early 2000s BBC documentaries uh, depicting dinosaurs and things, I believe it's the first episode that talks about a dinosaur called Platyosaurus, or Platyosaurus, however you prefer. Uh, that is a prosauropod. They still walked on two legs, but are very much bigger. They get to be,
I was gonna say, how big are we talking? Because that's at that point, it's the only thing I want to know is how big each step is.
they get to be, some of the earlier prosauropods tend to be slightly bigger than rhino, maybe a little smaller than elephant.
Okay, so conceivable by you know by what we know today.
Right. And so To this point, from what we can tell, they are already the largest land animals to have existed at that point. The prosauropods, only, maybe at tops elephant-ish sized, are already the largest land animals to have existed.
And this is where we need to cue Billy Mays. But wait, there's more.
Yeah, so they start off big. And you start to see, as well as them sort of just getting bigger, their necks get longer in, relative to the rest of the body. Their stance sort of shifts to maybe they could have walked on all fours if they wanted to. That's kind of debated at this point, whether they did that or not. It's kind of unsure.
Okay. It is not impossible either way, just based on their skeleton, though?
Right.
Okay.
Their hands don't seem to be shaped in a way that would indicate that they did that a lot, because they still had kind of the, primitive dinosaur grabby type hands.
Mm-hmm.
But they might have been able to do that a bit. But something that's really important that we will talk about is that their teeth start to shift from the normal teeth position, sort of all throughout the mouth, front to back,
Right.
to moving more toward the front and becoming a little simpler. The first, Sauropoda morphs had teeth with a lot of bumps on them that is good for, grabbing leaves and taking them off and chewing them and, grinding them up in your mouth as well as in your stomach with the gastroliths. But as you sort of move through time, their teeth get a little simpler, less bumpy, and start moving all toward the front. Then we get to the actual sauropods. It used to be, I believe, a class, but it is now just a clade, as we've talked about before. So it doesn't have like a formal, kingdom, phylum, class, whatever. It doesn't have a formal ranking like that. It is a clade. But
Right.
the clade Sauropoda, which was actually named by one of the people we talked about in our episode about the Bone Wars, Othniel Charles Marsh.
I remember that guy. Yeah, wasn't he was one of the two guys that were not too good.
Absolutely. But as I talked about in that episode, they did do quite a lot to establish, especially dinosaurs, as really interesting animals, and also just doing a lot of work naming them and describing them. That still sticks around to today, such as this entire group. So the first one that was found will not surprise you that they thought must have been an aquatic animal, because they were like, this is so big, how could this thing possibly have lived on land?
I mean, that doesn't seem unreasonable.
Exactly. And at the time, how would they have known any better?
Right.
This was 1878, I believe, is when he, first described this in like a formal publication.
Right.
So they had no way to know any better. To my knowledge, I believe the first species or genus described was called Cetiosaurus, which, if you Cetiosaurus, which means whale lizard. Because again, they thought it was aquatic. The only thing that they were like, okay, this is so big, the only thing we can really compare it to is whales. And so
Whales.
very quickly, they started finding more in as they moved into particularly Colorado and Utah with the Morrison Formation, which is sort of late-ish Jurassic. But by the time we get to the late Triassic, as I mentioned, sort of around 215 or so million years, we have the true sauropods. By this point, they are fully quadrupedal. They have necks and tails that are very long relative to the rest of their body. And they have adaptations for what is called graviportal living.
Go on.
Which means just being real friggin' heavy.
Graviport, like I assume that's like something based on gravity, just the etymology of that, graviportal living.
It might be some kind of Latin root, um, because I know the French word for sort of like fat, Mardi Gras, Fat
Mm-hmm.
Tuesday, is
Right.
GRA.
Okay.
There's probably a Latin root in there, but it's probably the same one that gravity kind of gets derived from as well. That wouldn't surprise me.
Right. Okay.
So just very, very heavy living. As we sort of talked about with elephants, they had really spread out toes and walked on their toes with probably a big cushion in the middle of where their palm would have been, particularly on the back feet. Um, Maybe not as much on the front feet. They didn't do as much of the load bearing as opposed to the back feet, although they still did obviously a lot.
Right.
So
Of course.
once we get to uh, true sauropods, they sort of break into two main groups with a couple sort of stragglers before that split. But so some of the stragglers are things that some people may have heard of. There's one called Volcanodon.
I have not, but now I'm wondering why we didn't do a whole podcast on Volcanodon. Like that.
But
That's amazing.
that was one from the early Jurassic of like South Africa, that general region of the world.
Is
So
there a
this,
reason they called it Volcanodon?
not to my knowledge. Sometimes it just sounds cool.
Oh, sometimes that's a good one.
Okay, a little bit of side tangent here. When talking about dinosaur names, so I am a little bit of a traditionalist in this sense, where I think like a name should be descriptive of the animal as opposed to just kind of memeing. Although there is one relatively recently named genus and species of Ankylosaur, which are the sort of squat armored club-tailed ones. Its name is Zool, Zuul. Yes, from Ghostbusters.
I didn't
And
realize that the people who were like naming the stuff were, meme lords. Like I didn't
absolutely.
think that that was a thing that I needed to consider. I thought that they were all, somewhat descriptive.
The species name kind of is. I don't know the Latin or what the actual species name is, but I know what it translates to, and it means destroyer of shins. So its name is Zool, destroyer of shins, because of its club tail, which would be about shin height for most of the large theropods that it was living alongside.
I love that.
Yeah, so just a quick, digression here. Um, some other more notable members of sort of this quote unquote primitive group would be Mementosaurus, very famous for having extraordinarily long necks, even for sauropods. Like other sauropods would look at this one and be like, "What are you doing over there?" Their neck probably made up somewhere around 50% of their total length, including their tail. So like their neck
Oh my
was
gosh.
as long as their body and tail.
That was their neck going kind of more forward, or was it going up like a giraffe?
They're more often depicted with it going up, not quite like a giraffe, maybe more at like a 45 to 60-ish degree angle.
Okay.
So not straight up like a giraffe or straight forward, um, but very, very tall. Like their necks were probably somewhere around, their head was probably around 50 or so feet off the ground.
Can
Right.
you say that sentence one more time?
Their head was probably somewhere around 50 feet off the ground.
Oh my god.
Just
This,
enormous animals.
man, this planet is awesome. All right, keep going.
And then Cediosaurus, the first one described, also is sort of in this um, still sauropods, but not the main group of sauropods group. Then we get into the Neosoropoda, and pretty much any sauropod that you can think of is in this group. And granted, this is a large group that has some more subgroups within it, but these are things that include your Brachiosaurus from Jurassic Park, Brontosaurus, if that is the name that you choose to give it, even though I don't believe that Brontosaurus is currently an acceptable name. Things to that effect. The much more familiar ones. They are broken up into two main groups. And sorry, it just suddenly started pouring here, so if you hear that in the background, I apologize.
It is no problem because there's somebody who's walking in the door right now, so we're just making noise all over the place.
Oh, okay. All right. But yeah, so the two main groups are the Diplodocoidia, named after the very famous Diplodocus, which is a genus, a very, very long, very large sauropod. This one goes for the length over height sort of metric. These ones are almost never depicted with their head sort of, or their neck going straight up, similar to a giraffe. They're much more horizontal. In fact, a lot more of the more recent depictions kind of depict their back legs being a bit longer than their front legs, so that their neck actually slopes kind of downward.
Okay, and like I assume that their kind of spine would do the same thing, like just because if the back legs are bigger, it would just slope down.
Yep.
Okay.
But even with that, their head was probably easily somewhere around 10 or so feet off the ground.
That I mean, that is slightly more conceivable, but is it really like just imagining a basketball hoop and there's a head up there? Like,
Yeah.
there's not a whole lot of animals
No.
that are that are like even ones
Today,
that we're
that is
familiar
just
with.
elephants.
And giraffes, I assume.
Oh, yeah. Yeah, I guess that's true. I kind of forget them because they're not actually that big. They're just tall.
Right. Right, but it's that is something in the course of this episode I was kind of going through my head and just thinking, what are some other really big just animals? And there's not a whole heck of a lot that's, at least taller than humans
No.
on any
Humans are
like
actually quite big animals.
right. You've got, your elephants, rhinos, giraffes, but
Hippos
like
are one that people
hippos,
kind of forget about.
right, yeah, certain kinds of bears, I would guess, but like, even at that point, you're already kind of straining. Most animals they might be faster or way more or any number of things, but they're not generally taller.
Yeah, not really.
Just in the course of this episode, it was just kind of what I was thinking. And then,
Mm-hmm.
we're talking about heads being, you know, orders of magnitude higher off the
Yeah.
ground than what we're used to. I'm sorry, go
No,
whatever you
you're
were
okay.
talking about. I completely forgot where we were, but just
So,
wow.
Diplodocus and its close relatives, Apatosaurus, is probably the more famous of its relatives, but they're well known for having exceptionally long tails, whereas things like Mementosaurus had the really long neck. Obviously, Diplodocus and Apatosaurus had quite long necks as well, but they're well known for having really long tails, to the point where, like, okay, and at the end it's so thin that we're like, what were you using this for? Because obviously things don't just kind of happen. It's like, okay, if you see a strange feature, especially a very pronounced feature, it was probably using that for something.
Right. Evolution doesn't happen for a reason, but if there's something there, it very likely has or at one time had a purpose.
Right. So some of the leading hypotheses for this might have been using it for self-defense, using it as a whip, essentially. And there's even been some biomechanical studies done that think that it might have been able to flick it and make a whip crack, break the sound barrier with its tail and make a crack like a whip.
What purpose would that serve?
Could be signaling to one another, just making sounds over long distances. Although we're pretty sure they were pretty good at that anyway, just with their, face making sounds the way normal animals make sounds. It also could just be a really loud noise, potentially if, while nothing was as big as them or even close, there were some things with really sharp teeth that were also quite big at the time.
Hmm.
So loud noises tend to scare scary things away.
That's kind of what I was thinking when you said break the sound barrier. Like I imagined that was more for other animals to get away or to stun them or to do any number of other things.
Right. There's also relatively closely related to these ones. They have much shorter necks, but there's is a family called the Dicreasoridae. They're well known for having really long spines coming off of their neck vertebrae that have, at various points, I don't believe it's the current interpretation, but it has been interpreted that they had two sails, similar to Spinosaurus, which has really long spines along its back. This one has two rows of spines along their neck vertebrae. And at one point, it was thought that each one of those rows of spines had a sail. That's not currently, I think, the favored depiction of them. But in one group of them, the spines sort of point backward, and the other one, they actually point forward.
So is this just nobody quite knows exactly what
We
was
have
going
no
on
idea.
with
We have no idea what these guys were doing. And so, along with that sort of group, we have probably the more famous ones, which are called this entire group is called the Macroneria, which means big nose. It might be descriptive, but scientists can be a little mean sometimes.
It's a good thing that my brothers haven't heard out about this name. Otherwise, that's what they would have been calling me all the time growing up.
This group includes things like your Brachiosaurus, the one from Jurassic Park, as well as most of the real big ones. Things like, and again, the sauropod names are out of this world incredible. For example, there is one in this group, sort of a subgroup within Macroneria called Titanosaurs. There's one called Giraffatitan. Pretty good. That's a good name.
Titanosaurus and Giraffatitan.
Yep. There's one that was.
Which one do I like best? Give me all of them. Like that. I was pausing there because I was trying to figure out which I was going to like the best.
Well, Titanosaur is the group that includes all of these.
Okay.
So this would also include things like Argentinosaurus, found in Argentina, Patagotitan, found in Patagonia in South America. Most of the contenders for the largest of these are in this group, as might make sense because they're called titanosaurs.
There's something about Titan or Titan, like there's something about hearing that just makes every name sound cooler.
I don't believe we actually have a good reference for where this one goes, but this is my favorite sauropod name, so arguably my favorite dinosaur altogether.
Here we go.
Its name is Sauroposeidon.
Sauroposeidon. Does that have anything to do with, water?
No. But, however, that is not the only thing that Poseidon, the Greek god, was the god of.
Teach me.
Poseidon was also the god of earthquakes. Because in Greece, the Mediterranean is where the African tectonic plate and the European plate or Eurasian plate meet. So there's earthquakes there, and the Mediterranean Sea happens to be where that plate boundary is. So earthquakes happened from the sea to them when they were, developing their mythology. So Poseidon also became the god of earthquakes. So what this means, Sauroposeidon, means lizard earthquake god.
Lizard earthquake god. All right. I see. Yep.
Excellent name.
I see it. Oh my gosh.
So that is sort of the diversity aspect of sauropods. So let's talk about some of the things that you've sort of asked quite a few questions about. How and why? Oh, that thunder is really going.
That's outstanding. That was the earthquake god. That was,
exactly.
I was doing that.
Well, Brontosaurus does mean thunder lizard. So here we go.
Boom.
So again, just how did they get this big and why? Like, as we've talked about in the elephant episode, at any given opportunity of not being that big, elephants lost it. There were many different species of dwarf elephants, as we talked about. So being big has a real cost. Obviously, it has some benefits, or things wouldn't keep doing it, especially to the extent that the sauropods did. So, how did they get this big? Sauropods are really complex animals, as you probably assume. So it is not they did this one thing that let them be very big. It is a combination of many things, because they do a lot of things that a lot of other animals also do, but no animals really do too many of them at a time.
Right, so you might see some of these features in other animals, but just not all at once.
Right. So
okay.
The big one is, let's talk about the not obvious ones first, because obviously their neck is kind of the outlier. No other animal really has a neck like them. So we'll leave that one for last. So they were the first ones to really do sort of leg structure for being big correctly. There were some previous really large animals, not quite as large as some of the early sauropods, but they had their legs sort of sprawled out to the side in the more typical lizard position, as opposed to sauropods, who, like mammals, bring their legs underneath their body, which is much better for supporting weight just from a physics perspective. That's why when you build a building, you make the weight-bearing columns, straight up and down.
Makes total sense, especially given the mass of the animals we're talking about.
Right. So another thing that that is not unique to sauropods. All dinosaurs pretty much do that. Mammals do that. None of them ever got this big. They do something that also most dinosaurs do, which is they have pneumatized bones, similar to what we talked about with pterosaurs, where they're not quote unquote hollow. What they do is they sort of take the bone, say that mammals have, which is solid around the outside, then spongy, squishy sort of in the middle, which is where your blood gets made, essentially. They take all the spongy, squishy stuff and put it inside a bunch of struts inside the bone. So what that does, it lets it be stronger while not becoming lighter, or without becoming heavier, without just becoming more dense.
So they take the less dense part and put them in, and it's in like specific areas inside the bone.
Right. It's essentially, if you've ever seen like a big, or I guess like the arm of a crane, you know how there's sort of all the like zigzaggy bars of metal that are there
Right.
for structural support?
Right. The
That's
trusses. Yeah.
essentially what they do inside their bones.
That seems awesome.
It adds a ton of strength without making them heavier.
Right. A ton of strength, like efficiently.
Yes. So that allows them, elephants don't do that. So similar to what we talked about with sort of how birds can only get so big because of their big beefy legs last episode, elephants might only have been able to get so big because they didn't have that kind of bone. And so for them to get bigger, they would have to get bigger, denser bones. And then there's just a cost benefit and diminishing returns once you get so big with that kind of bone. Whereas with sauropods, they could just make their bones and add more struts and make them as strong as they needed to without making them much heavier.
Are there any animals today that do that with their bones?
Pretty much just birds.
Okay.
Because I don't believe bats do it. They might, don't quote me on that, but to my knowledge, it's only birds.
Gotcha. Gotcha.
So they also, like birds, we're fairly sure, had air sacs in their bones. So it's like, yes, they were sort of hollow, but it's not like they were. The bone itself was not filled with air. There were sacs inside the bone that was filled with air. Kind of a technicality, um, but sauropods kind of take it to the extreme. Whereas with a lot of other types of dinosaurs that we can tell had this kind of thing, we're like, okay, they had it sort of maybe around their vertebrae in like the back area, the chest-ish area, maybe some in their skull. Sauropods took the whole air sac thing that some other dinosaurs did and just kind of turned that to 11. They had them
Oh
sort
boy.
of around their ribs. They had them all along their entire neck, that giant long neck. The Macronarian ones, sometimes you'll see them depicted with like their nostrils at the top of their skull. We kind of think that that's not what it was for. We think that there was probably some kind of air sac or just a really large sinus there that they used maybe for like a resonating chamber to make loud noises. We think dinosaurs were actually quite noisy. As
What do
well
you
as,
mean by
but
what do you mean by quite noisy? Like,
they just made lots of sounds. Birds are quite noisy today. They communicate with each other a lot,
mm-hmm.
or even, with you, like a goose will
Right.
honk at
Okay.
you very much. So we tend to just think dinosaurs in general were quite noisy animals. And so that's probably what the big nose holes in the top of like a Brachiosaurus skull or something was for, making noises like that, but also just having a pretty good sense of smell as well.
Okay.
But they had these air sacs all over the place, which A, probably helped lighten their bones a bit, but it's not like you were filling them with helium. You know, they weren't a balloon.
Right.
But they were, like with birds, integrated into their breathing system. All of these air sacs in their bones were basically reservoirs of fresh air. Because when we breathe in, you know, you breathe in fresh air and you breathe it out, but it all comes from the same place, sort of, right? It goes like in and out
Right.
the same direction.
Right.
Whereas
And
with
remember you talking about this in one of the other, and I forget the end of one of those other episodes where it was,
that was the episode about flight.
that was right. Yes.
But with birds, it all flows sort of in a loop. So their lungs and, you know, all the rest of their tissues basically constantly have fresh air. Sauropods very likely also had this because that might have helped contribute to their large size, because you need oxygen to fuel respiration. You know, anything that your cells do, you make your energy from oxygen. So having more fresh oxygen means you have more energy to be gigantic.
And that makes total sense when you are of the size that we're talking about, to do things in that more efficient way to get that energy to all those parts of the body. Like that seems like the better way to do it.
Right. And then we have the more obvious thing about how they might have gotten so big. Oh, actually, there's one more footnote that I forgot. Another thing is potentially how they had babies. Because elephants, as we talked
Cue the
about,
swanky music.
not how they made the babies, how they had the babies.
Go on.
Elephants need to carry a baby. You know, our modern elephants are pregnant for about just under like 2 years. Some of the bigger ones might have been longer because they needed a bigger baby. You know, you were a bigger
Right.
animal, you have bigger baby.
Yep.
Sauropods, from what we can tell, laid eggs like every other dinosaur. And from what we can tell, were not good parents. They just laid their eggs and left. Which means if you don't have to carry around another one of you inside of you, that frees up a whole lot of weight.
So could they have just like kids more frequently? Could they make more of themselves more frequently because they weren't carrying it around?
So they pretty much did the sea turtle strategy, where they just lay a bunch of eggs at a time.
Okay.
And only a very small fraction of the total eggs laid will actually become adults. So
right.
that's how we kind of that might have been obviously not a main contributing factor, but a factor on how they got so big.
Mm-hmm.
And then we can't not talk about that, you know, from the shoulders up. So the way it was described to me in one of my classes was a term that was new to me, called a feeding envelope, or
That's
envelope if
new
you
for me
prefer.
as well.
So it is essentially the area that you can reach for food without moving. So your feeding envelope is from wherever you are sitting, in your recliner or on your couch or wherever you happen to do your relaxing, all the food that you can reach around you without getting up.
Forgive me here, and whatever scientist invented this, but why is this useful?
Because for animals, it essentially allows them to maximize the amount of food they can eat while expending as little energy as possible.
Oh, this is basically a measure of efficiency.
Yes.
Oh,
So
okay.
sauropods would basically walk up to a forest. This is why we think their neck was so big or so long. They would just walk up to the edge of a forest
Mm-hmm.
and just vacuum up all of the leaves without moving, just by moving around that big honking neck of theirs.
Right. Okay.
And so they have many other adaptations to support this. They, like I said earlier, their teeth were all basically in the front of their mouth, and very simple. There were a couple exceptions to this. I believe Brachiosaurus had some like leaf-shaped teeth that were good for shearing, but by and large, they all had very simple, very like peg-like teeth. Because they did not chew. Their job was literally to just inhale as much food as they physically could.
Is that where like the stones come back and, because they're not chewing, like the stones, aid in that kind of mechanical digestion?
Absolutely.
Okay.
And also, this is just kind of an assumption. I haven't seen the actual data to support this, but this is just kind of an assumption that is pretty common. So there's got to be some kind of data to back it up. But they were probably had a very efficient sort of like fermentation process in their gut, similar to cows. But, or even potentially more efficient because, cows don't get the size of buildings. So
not yet.
Don't know. That's a nightmare I don't want to have. So they are designed to drop themselves in one spot, eat as much food as they possibly can, as quickly as they can, as efficiently as they can, move over to the next spot, just beyond where they could reach before, and do it again. To the point where some of them, particularly members of a family called the Brachiosauridae, had mouths that flared out in the front, sort of like a vacuum cleaner head.
Okay.
To be real wide, to get as much food in their mouth per chomp as they could.
This is, we've talked about why animals don't get this big, but if you're going to do it, do it right.
Exactly.
This is the way to do it.
So between their efficient breathing, their efficient eating, their efficient digestion, their really light for their size bones, that all of these combination of things are why they got so big. Plus, it helps when you have big predators around as well. Because if you're already big enough to avoid being eaten by the biggest predator, why would you get any bigger?
Yeah.
So, that is kind of sauropods in a general nutshell. But there are a couple that I want to highlight. Some of the big ones, and also a couple actually quite small ones.
Okay.
So like I said, some of the very large ones, things like Argentinosaurus, things like Patagotitan. I talked before how they might have been somewhere in the realm of 60 to 80 tons.
Just you even saying that again, I just need to take a minute. Just
some estimates, and these are not the most sort of popular assumptions, or sort of speculations. Some of them have been nudged closer to 100 tons for some of the gigantic ones.
100 tons?
And for comparison, blue whales weigh somewhere in the realm of 170, 180 tons.
And it is possible that that's happening on land. Not quite, the blue whale side, but on land?
Yes. And weirdly, one of the cool things about sauropods is that, so with elephants, all the ones that got gigantic were closely related to one another. All of the really big ceratopsians, Triceratops and friends.
Yep.
All the biggest ones of them were relatively closely related. Generally, all the biggest members of a group are relatively closely related to one another. With sauropods, no. Each group had a contender for the largest land animal of all time. So like
really?
Argentinosaurus is a titanosaur, one of those macronarians, one of the more derived ones from the end of the Cretaceous period. Like
Right.
the Mementosaurus, also somewhere in the realm of 60 to 80 tons, one of the ones that where half of their body is their neck, that lived somewhere around the late Jurassic, early Cretaceous. You know, somewhere around, at minimum, 60 million years before that. So, Diplodocus had some specimens that are estimated very closely to that as well. And none of these are particularly closely related. Every group has at least one, usually a couple, contenders for the largest land animal of all time.
And they were all around. You said they were all around like at different times, correct? Like different periods.
Absolutely.
So just this evolution of getting that big happening over and over again with these different groups at different times, like that's nuts. And so I don't know how much more you have, but I am curious as to kind of the demise of these guys. Like, was it, how much do we know about, do we think it was the asteroid? Do we think that there was something else that was, kind of going back to that paper you referenced at the beginning, that was sort of taking them out as, before the asteroid came? Like, because it seems as though they were doing, if if they kept evolving like this time after time over this many millions of years, it seems like something must have been going okay for them. And so I'm curious as to, like, why aren't they around anymore?
I think a big part of it is, you to have this much body mass, you need to obviously eat a ton of food.
Right.
And so they kind of weren't doing all that well toward these ones in particular, sauropods, I kind of think that weren't doing all that hot toward the end of the Cretaceous anyway, with the exception of the titanosaurs. They were doing quite well down in South America, and I think there were some in Africa as well, and potentially some in Antarctica, I believe, as well.
Uh-huh.
But in North America, sort of the latest Cretaceous stuff, where Triceratops, Tyrannosaurus is from, I don't believe there are any sauropod fossils in that kind of related succession from around that same time.
Okay.
So in some areas they were doing great. On the southern continents, it seemed like they were doing pretty well. But in the north, it's kind of mixed. And
And it
so, oh,
just
go ahead.
something that large event, it may be doing well for a while, but at some point it's just going to kind of, start to run into a limit.
Not necessarily. I think it was so when the end Cretaceous mass extinction happened, the first thing to go were the plants.
Mm-hmm.
And so if there's
No sunlight, right?
right. And so if the plants are gone, very quickly, the very large thing that needs tons and tons of plants are going to be some of the first things to go.
Right.
Whereas some of these small things, maybe some small herbivorous mammal at the time that only needs, say a pound of food per day, if that,
Right.
or potentially that even eat seeds, which, seeds can last forever, so they
Oh,
can
really?
kind of just go, not forever, but
Quite a while.
years anyway.
Mm-hmm.
So they could just kind of be running around in the now dead and or dying forest, running around eating seeds and things for quite a while and probably be fine. Whereas if their forest is now gone, sauropods will also go quite quickly.
Right.
Uh, but I have a couple more sort of quick facts about
Okay.
sauropods. Only two more. I know this episode's getting a little long.
No,
But
bring them on.
so some of these gigantic sauropods, particularly those titanosaurs, have one of the weirdest adaptations that I still don't really understand how it helped them, but it must have. So take a look at your hand if you are able.
I am looking at my hand, as is my girlfriend's dog.
You have your forearm, which is your radius and ulna.
Right.
Your wrist bones, which are called your carpals.
Mm-hmm.
The bones in between your wrist and where your fingers start. Those are called your metacarpals. And then the bones in your fingers are called phalanges.
Which is a great name.
It is. What some of the super giant ones did, they show a general trend in reducing the size of the phalanges, or reducing the number of them. And then there are some of them that just ditch all of the phalanges altogether and walk on the end of their metacarpals.
Really?
They were walking essentially on their first knuckle. So, like when you make a fist, the ones that, are in the same line as your arm,
Mm-hmm.
they were walking on those.
So what does a horse do?
A horse walks on a single, their middle finger, on the very
Right.
tip of their middle phalange, or phalanx, I guess.
Okay, but they're still not walking on their back knuckles. They're still walking on
They're walking
the
on a
equivalent.
toe.
Right. Okay. Whereas these guys just got rid of them altogether.
They just ditched the fingers. And so there was obviously still some kind of padding or something there. But like I have a really hard time understanding the physics of why that was beneficial for them. But that's just a trend. And that's not like, oh, this one, we just don't happen to have the fingers with it. We've gotten many skeletons that say, okay, these ones just didn't have fingers.
Right.
So
At some
that's a
point,
consistent
yeah.
thing.
Absence of evidence is evidence of absence at some point.
Right. So that is just one weird, quirky fact. But when we've spent the entire time talking about some of the really, really huge ones, let's talk about some of the little tiny baby guys. And I don't mean
Okay.
babies, I mean island dwarfs. Because they also had some of these. They're much fewer. I suspect there were more of them. We just don't have the fossils. However,
Seems
I
reasonable.
was able to find two, I believe. At least ones that were like documented to be dwarfs, not just small.
Okay.
So there's one called Europasaurus.
Found in Europe, I assume.
Yes, it is
Okay.
found on what has since been named Hatzag Island, which I also kind of referenced last episode, with a
Mm-hmm.
giant pterosaur called Hatzagosopteryx,
Right. Right. Right.
which was a gigantic pterosaur, which was probably the apex predator on this island. Europasaurus was teeny tiny for a sauropod at just about 20 feet long as a full grown adult, and somewhere in between 1 and 2 tons. For a
And
sauropod, that's
these
real
are the
little.
small ones.
Yeah.
That's what's not, like these are the small ones that were on an island and adapted to live yada yada. But still.
The smallest they got was a really long cow. that was maybe rhino. I guess rhino might be a little more appropriate for that kind of weight,
Uh-huh.
but somewhere between a cow and rhino size. But just a super long, stretchy cow rhino, and that's as small as they ever got. And I think that about brings sauropods to a close for me.
That is, like most of what's great about these is like just comes from their size, and yet still it doesn't get old. Just hearing, and what they were able to do with their size, whether it was their breathing or their bones, how they made them strong, or like it all kind of relates back to their size, and yet like that doesn't get old. Just hearing about these guys and just with the size of sauropods and how they were able to make that happen. It's just nuts. And I love it. And I love the fact that you brought this into this episode.
Absolutely, I just love them so much, just because
They are your favorite dinosaur, correct?
they are. Just because I don't understand. And granted, I'm not like a biomechanics person. That's not what I do.
Mm-hmm.
But just the sheer physics of being that large, like for a pretty substantial amount of time, we thought, okay, these were animals that must have lived in lakes because they are so big. We thought that's why their neck was so long, so that
It's the only thing that makes sense.
they could walk on the bottom and snorkel at the top. We thought that's what they did.
Right.
But, with better biomechanic stuff, we're like, nope, these things were built for walking, and that's just what they do. And so, this is my favorite group of animals. Thank you.
I can tell, and I know you're not much of a dinosaur guy, but this was well done, and I am glad that we had the opportunity to talk about them.
Well, thank you for letting me. I appreciate it.
No problem. This has been episode 30 of I Wish You Were Dead, a podcast about things that used to be alive. Thank you to the thunder, which just clapped a couple of minutes ago outside my window, in addition over by Gavin. Thank you to Bella, my girlfriend's dog, and everything else that made noise in the background today. And thank you especially to Gavin for week after week giving us the most interesting things to learn about that I could ever ask for.
Absolutely, Mike. See you next week.
We'll see everybody next week. Take care.